Okay, I am going to move on in Griffith's book and now get to section 1.5 about momentum. But first we're going to talk a little bit about the expectation value, as he has done right here to open up this section. So we did use this result, this equation 1.28 before, to find expectation values in some problems. But to kind of go into the expectation value in a little bit more details here, the expectation value we always mark in this sort of bracket. And just to make a subtle distinction here, it doesn't mean that you measured the particle, the position of the particle over and over again. It does not mean that. This is the average of the results that you would, it's not the average of the results that you would get if you just took a quantum particle and measured its position over and over and over again. That is not going to return you the expectation value. And that's because if you have like some wave function over space, and we're looking at some particular position, my wave function is existing in all space. So if I measure it at, say, x equals a, I have then collapsed the wave function onto point A. So if I measure the position of it again after I've collapsed the wave function, I'm just going to get the same position if I do it quickly enough. Instead, what the expectation value would be like if I had some particle with some wave function and I measure it, thus collapsing it at, say, some point A, and then I return it to its original state, and then I measure it again, and then I return it to its original state and then measure it again. And if I do that infinite number of times, then the average of those results are going to give me the expectation value. Or you could say that the expectation value is the average of measurements performed on particles in all state psi. So you either found a way of returning the particle back to its original state and measuring again, and so forth, or you took an infinite number of particles, or a whole ensemble, as he says, that each have the same wave function, that each have the same state psi, and you performed a measurement on all of them. So you can either take one particle and keep returning it to its state and measuring it again and again, but you have to always return it to its original state. Otherwise it will be collapsed upon the where you measured it. Or you take an infinite number of particles and you measure all of them, and then the expectation value is going to return you the average of those results. Now, of course, in any real-world system, you could have a very high number of particles. The nice thing about quantum things that are going to be determined by quantum mechanics, things like atoms or electrons, you generally have a lot of them. You don't have an infinite number, so you're not always going to have a perfect mathematical agreement, but if you had a high number of particles and you measured all their positions, and then you built a histogram of those results, maybe it looks something like that. then the expectation value is going to be the average of that computed histogram. So we can take this is just in terms of position that I'm using this analogy here, but expectation value can be taken for any physical quantity. So this section is about momentum. So we have taken expectation value with respect to position before, mostly in order to determine what our standard deviation is. But now we want to look at, can we do the same thing with other physical quantities? i.e., what if I want to know something about, how it's moving? What if I want to know something about the velocity? Now, keep in mind, we're going to be looking at the velocity of the expectation value. So instead of just dx dt, from here, we are instead going to be looking at the time derivative of the expectation value. And that's because before we collapse our wave function, it's existing in all space. The position is not well determined until you collapse the wave function. Since the position is not well defined or determined, then we clearly can't have a well-defined velocity until we collapse the wave function. So if we want to compute a value for that, then instead of considering something that's very ill-defined, we're going to compute the value for the time derivative of the expectation value. And that's where Griffith starts right here. But there's a couple steps that he glossed over that I wanted to make more explicit. So the first thing that he does is the same trick that he did before, but I will go over it again in a little bit more detail. So our expectation value of x, I'm going to just put it in here, is going to be x, the integral of x times the absolute value of the wave function squared. So, and we can always write that. I'm certainly in the habit of writing it like this. So that's just my preference there, but we will start with this guy. Now, if I want to write the time derivative of that, I have my full derivative on the outside of my integral. And then I can put that inside my integral by taking it as a partial derivative with respect to time. Okay, now we need to, same thing we did before, looking at normalization, we need to actually look at like our product rule on this guy, right? Or chain rule. And so I have, and this is where it might be more convenient to pull out that x. And then I'm going to have d psi complex conjugate. We're going to stick with the same order. So we can keep it a little bit straight here. So we are going to have psi d psi dx minus d psi complex conjugate dx d psi. Just as we did back with normalization, right? So we start just by parsing this guy out. You get the two time derivatives there. So alright, I'll just leave that up, I guess. There we go. Okay, so when we parse this guy out, complex conjugate times psi, we are just making that more explicit here like this. So for my expectation value, my time derivative of my expectation value of x, I'm just going to back up. So, you know, if I'm not going to skip steps, how about I don't skip any steps, right? That would be nice. So I'm going to work that guy out right there. So all I did was, instead of writing this, I'm going to write the second term, which is just writing out the, time. If I take a derivative of two functions, then I need to take the first function times the derivative of the second function plus the derivative of the first function times the second function. Then we have our Schrodinger equation. You can go ahead and make that smaller. Let's go ahead and make it really small so we can really zoom in here. So our Schrodinger equation has d psi dt equals this guy. So d psi dt equals I h bar over 2m, second derivative of psi with respect to x, minus I h bar v psi. And then my complex conjugate is just going to be negative because it's a complex conjugate. We take a negative of the imaginary part. And now that negative turns into a positive, and we get that guy. So now my time derivative is just going to be dx x, and then we're going to have all this stuff in here. Complex conjugate psi times all of this minus complex conjugate of psi I over h bar b psi. Then we have plus all of this times psi plus h bar v naught psi complex conjugate, and then psi. There we go. That whole thing there. That then is going to simplify because these terms, well, our potential energy terms, are going to end up canceling out. I have a negative, I have a positive, so those conveniently canceled out. So this guy equals, and we have our x out there, and then these come out together. I can pull out that I h bar over 2m, and I get a complex conjugate psi second derivative minus that second derivative of the complex conjugate, and then psi. I can then pull out again another d dx. And we get where Griffiths started. So we did all that work just to get where, like, he started, seriously. Which I do realize might be more than a little bit pedantic, but personally I find it helpful, which is why I'm doing this anyway. Okay. Now, we are going to integrate this by parts. So this is where we are starting. So I am starting on equation 1.29, where I have the time derivative of the expectation value of x equals I h bar over 2m, integrating over x d dx, and then this guy. Now here I'm going to go ahead and I'm going to break this into two integrals to make this a little bit easier to see. So I'm just going to take this integral and then minus the second integral. So then we have minus this second integral. They're both times the same constant, so I'm going to keep that out there. And then I have x d dx. And now we have the x derivative of the complex conjugate times psi. And we end those parentheses. Now, we're going to use integration by parts, but we're only going to do it on one term. So I'm going to use integration by parts on the second term, and I'm going to leave the first one alone. Because I want, I'm going to do it. I don't know why I wrote first term here. I think I meant the second term. Okay, so integration by parts, if you forgot, you're going to want to remember real quick. So if I have an integral of some u dv, I can break that apart into uv evaluated at the limits. So in this case, my limits are positive infinity and negative infinity, minus the integral of v du. So here, just on this second term, I want, yep, that one's right. So I want my u to equal x. And then du is just going to equal 1, or 1 dx. So that's my u. And then dv in turn equals this. Meaning that v just equals this guy. Maybe I did want to do the first term. We'll see. I can always check how I did this before. Alright. We'll see how it works out. Maybe my note was right and I did want to do it on the first term, not the second term. But that's what I'm going to get for not trusting myself. Okay. Actually, I think I'm going to go ahead and do it more. Hold on. We are going to go back a step. And we're going to do this more general. Let's go ahead and write this all as one integral. Okay, so I'm going to just have this guy. Like this. Now let's go ahead and do our integration by parts on just the first one. Like just the way it is right now. So I have u dv equals uv evaluated at the limits, and that's going to equal v du. My u term is going to be x, so the derivative of x with respect to x is 1. Thus my dv term is just going to be this guy. So let's just get rid of this partial derivative first before we go and try to break it up. Let's just get rid of it. And then that's going to be minus d psi complex conjugate dx psi. If I integrate that with respect to x, then I just get the term that's inside the parentheses. So let's take this simplification step first. So that means once I go to here, I have my I h bar over 2m. That's going to be times, instead of this integral, I'm going to have it evaluated at the limits. So that's going to be u times v, this whole thing, evaluated at negative infinity and positive infinity, minus my integral of v, which is going to be this guy, and then that's going to be times du, and my du is just 1. Now my integral converges. One of the conditions of having our wave function is that it converges, meaning that if I evaluate psi at negative infinity, it equals 0. Psi at infinity equals 0. So I'm just going to get 0 minus 0. So since this converges, that means the whole thing's 0. And now we've cleaned it up quite a bit. So if you don't remember integration by parts and you're taking quantum mechanics, you're going to remember it real quick. Okay, like get used to it because there's a lot of it. So then I have dx, and we get this guy. Okay, much better, right? So, and if you don't like minus signs, we could go ahead and move that I to the bottom. I kind of find them a little bit confusing, especially when we get into i's. So I'm just going to go ahead and move that down because I feel like it. All right. Now we're going to do integration by parts on the second term, and I was wrong with my note. I do want the second term. I don't want the first term. I don't know why I said I wanted the first term. Okay, so my integration of parts, I always write it out because I can't ever remember anything, even considering these that I worked out. Like yesterday, I don't remember it, so I work it out again. So I write it out. I don't have any like math balls on that. I'm just gonna write out the equation. I'm gonna do it my way. Now I want u in this case. So I have u and du, and I'm gonna have v and dv. Now my dv is going to be this guy, and you may wonder, why am I doing this? Because you might see where it's going and think it's dumb, or you're going to see where it's going and realize we're going to get where Griffiths got. So my v is going to be the integral of d complex conjugate dx. So I just get complex conjugate as psi. And then that means that my u has to be psi, so du is just d psi dx. So now my time derivative of my expectation value is h bar over I to m integral dx. Our first term was the same. And our second term is now, so we have minus u, which was psi, times v, which was psi complex conjugate, evaluated at our limits. That's going to be 0. And then that is going to be minus a minus. So that is now going to be plus integral dx of v, which is complex conjugate, du, d psi dx. And I should probably just put those in brackets to be better about it. This one converges, because that's what wave functions do. So it's 0. And now Now this guy equals h bar over I to m. And now we just have our integral dx psi complex conjugate d psi dx plus psi complex conjugate d psi dx. Meaning these are now like terms. I can add them together. So I'm going to get, now this is a pedantic step to write out, 2 times this guy. The only reason I'm writing this out like this specifically is that this is where students have, well, probably back at this point, they have the most temptation to start to do magic math. And this is a very easy math step to show, and to be honest, if I were grading it, I would really look to make sure that you included that step and that you're not just, you know, waving the magic math wand because you know what the answer is supposed to be. Personally, those twos cancel out. And what we get is h bar over im, and we have our integral dx of psi complex conjugate, and I'm going to write it like this, d dx psi. So this is the velocity of expectation function in space. Expectation. So, I said, even Griffiths makes sure knows that you're talking about the velocity of the expectation value of x. It does not equate to the velocity of the particle moving through space, because that particle's position in all space before the wave function is collapsed is not well defined. So if the position isn't well defined, then the velocity doesn't really mean much. Even as he says here, it's not even clear what velocity means in quantum mechanics. If the particle doesn't have a determinate position prior to the measurement, it can't have a well-defined velocity. What it does mean is that if instead of your measurement being a measurement of position and you collapse the wave function to be at the expectation value, your measurement is that of velocity, this is the reading that you're going to get on your instrument. This is, by the way, just a different notation for your product rule and your integration by parts. So if the U's and V's were not familiar, then you probably saw it like this. Okay, now momentum. So we know that velocity is related to momentum. Momentum P, and that equals mv. That's like from semester 1, physics 101 or physics 1010 or high school physics, whatever you want to call it. You learn that one pretty early on in physics. Basically the definition of momentum is that it's the velocity times the mass. So in terms of our expectation values, our momentum, expectation value momentum, is going to be mass times that whole chunk that we just did. So that's going to be mass times, going to put in this guy now, integral dx, oops, I forgot my constants. You know, I'm just going to put them in the middle. Why not? H bar over I m d dx psi, and that's complex conjugate. Now we can cancel out our m's, and I'm going to write that as just expectation value of P of momentum is going to be integral dx complex conjugate psi h bar over I d dx acting on psi. Yay, that's very happy. So this gives us a new, much more useful way to look at momentum. Instead of looking at momentum as mass times velocity, now I'm looking at momentum in a different way, which is h bar over I del x. So this is an operator definition of momentum. So whenever I have momentum, I have this partial derivative with respect to x, and it needs to act on something. So I have to apply this operator of momentum on the wave function in order to get the expectation value of the momentum. And operators are going to be the way that we look at these properties in quantum mechanics. So we could say like the operator of x, that one's easy. So our position operator is just x. So if we are looking at the position of something, that just means we multiply it. We just have x there. Our operator of momentum, however, involves us having to take the derivative with respect to space to it. And we're going to be using this sort of approach for like the rest of Griffiths. And if you go on and do like Landau and Lifshitz book, like you're going to be using operators. So this is just a different way of looking at things that we've done before. So he does a couple examples in here where he says, like, you know, the like kinetic energy T. Classically, we looked at that as being, you know, 1/2 mv squared. I can go ahead and multiply that top and bottom by m, because it's the same as multiplying by 1. And I get p squared over 2m. Now I look at that in terms of an operator, or in terms of an expectation value, using this definition of p. He also has angular momentum, which of course is not going to be in one-dimensional systems at all. So if we wanted like an expectation value of kinetic energy, say, then you would be looking at doing dx psi t psi complex conjugate t psi t we have as this guy over 2m, but we want to write that as an operator. And by the way, for operators, order does matter. Multiplication order does not matter, but for this sort of operator, it does. So it's going to depend. We'll get into this more. I believe it's chapter 3, which is the formalism, where we're going to look at commuting properties of operators. So that means our t is just going to be h bar squared over I squared. That's going to make it negative. I squared is negative 1 over 2m. And then we are going to have the second derivative, meaning that our expectation value for kinetic energy, for example, is going to be this. Negative h bar squared over 2m, second derivative with respect to x, acting on psi. Or you can pull out the constants the way that he did in Griffiths. There's certainly nothing wrong with that. So any dynamical quantity for a particle in state psi, you can find the expectation value using this. So, for example, if we had something that was, he put it in general here. So if you had something, some sort of quantity that is a function of, say, position and momentum, if we want to find the expectation value of that, then we are going to take the integral over space. I'm just using one dimension here. I suppose I should use R to be general, that it's for 3 dimensions, but I think you pretty much get it. I'm going to use our operator for P and then psi. So that's just in general. That's any old expectation value. Now you may wonder why I go over in so much detail over momentum instead of like kinetic energy or some other term, and that's just because momentum is much more useful. So we're going to be looking at a lot of stuff in terms of momentum. If you go on to do condensed matter physics, most of your calculations are going to be in momentum space, so it turns out to just be more useful. And that is it for section 1.5, all about momentum. Our big result is this operator definition for momentum. Our expectation value is this. So this is our new way of thinking about momentum. And we're going to be keeping that around. Okay, next we will have a couple of problems. Problems 1.11 and 1.12 and 1.13 are all going to be all about momentum.